Alright, so as I was saying, the first law, an object in motion must stay at rest unless it acts. Oops! An object at rest must stay at rest unless a force acted on it. Or an object in motion must stay in motion unless a force acts on it. But in general, the velocity of an object will not change unless a force acts on it, which means it won't change either direction or speed. The momentum cannot change. Whatever way you want to phrase it, the pattern of motion of the object cannot change unless a force acts on it, which means if something is changing, there must be a net force. Which is why when you're inside a car and you see the bubbly head that didn't used to be moving, something moving to the right, you say there's a force acting on it. Well, in that case, that's the problem. There's a force acting on you, which is and not on the bubbly head. We talked about this last class, right? And then it makes it look like the bubbly head is moving, because that's a relative motion thing. You're the one that's initiating the force who the force is acting on. So relative to you, it seems like he has a force acting on him. But it's very important that these laws only hold constant if you are in an inertial frame of reference. That means the frame of reference that's looking at the problem is not moving, right? Stationary, or actually not necessarily stationary, not accelerating. All right. So if the frame of reference is not accelerating, then you can look at it and use it as a frame on which the laws will work. But since you are in motion in the car, you are accelerating, you're turning, right? The laws won't apply from your frame of reference, and it seems like the thing is moving without a force, right? So but really it's because you're the one that's actually accelerating. So that's just based very clear on that. Second law, you know second law?
I think within.
Something? No? Yes? Okay. It's basically what? Second law? Don't look down. You don't know the second law? We just have a serious issue here. Yes, second law?
F equals ma.
What does that mean though?
Yeah, that's what I put.
Force is equal to an object's mass.
That's not what he's trying to say, yes.
Okay, the acceleration is proportional to the force that acts on the object and
Inversely proportional.
Inversely proportional to the mass of the
It's
object.
actually not about force. It's not F equals ma. It's A equals F over M. That's really what the force is about. It's actually called the law of acceleration, right? The first one is the law of inertia, right?
Yeah.
The second law is the law of acceleration, which basically says how much. So the first law says why things should not change. Are you with me? The second law tells how things change. So how do things change? Proportionate to the force, the net force that acts on it, and inversely proportional to the mass. Why inversely proportional to the mass? We talked about this last class. Because mass is the. What is mass?
Oh, it's like
It's the quantity of what?
Oh, it's a quantity of inertia.
Quantity of inertia you have, or the object's resistance to change because of force acting on it. Now, it's a natural property that the matter has, right, of resisting that thing. So remember, the first law is about what shouldn't change, right? So there's no net force, there's no net change, right, on the motion pattern. But the second law is how does the motion pattern change? Well, so they're kind of like the inverse of each other, right? What does the third law says?
For every action, there's an opposite.
Yeah, but everybody says that, but what does that mean?
That if I push off you, I'm pushing like off of you of that force, and you're pushing.
Right.
no force.
Okay,
There's
but
force
I
pairs.
told you guys that this was a statement of what?
The law of force pairs. That's what I
What last class I said it was basically what?
Energy of
Conservation of energy.
Oh.
Why is that? What is that? Because if I push something and it doesn't push me back, what I just do? I created energy, right? And I can't add energy to the universe. So when you look at what does that mean about forces in the universe? What is the
They're
net?
all paired.
They're all paired. Very good. That's another way of putting it. Very good. All right. Let's make sure we can do problems with that though. This is what this is about. Okay? Which friction is stronger?
Static.
Why?
Because
There's no word to oppose.
What did you say?
Because I guessed it against straight.
Because you guessed right. Okay.
Wait,
It takes
because the
more
microscopic pieces.
There's more bonds
And
connected,
then
right?
And
Okay.
kinetic friction
Kinetic-
takes place when it's already moving.
Right. So there's less electrostatic
Less time
interaction,
for the bonds.
or less time for the bonds to form. All right. Whichever way you want to think about it, but in practical mathematical terms, the coefficient of static friction is bigger than the kinetic one. So as soon as you start moving, the friction goes down. Right? Okay. Next one, number 3. Let's do that one. Anybody has this?
Yeah.
I have the fruit.
I have
Yeah,
the
somehow
You wanna try to do it?
like-
I have,
yeah.
Okay.
I have the equations, but can you check them to see if they're right?
We'll see. We'll find out in a second. All right. So, anybody has done the 3 bar diagrams for 4?
I did that too.
All right, so try to do that. You do 3.
Okay.
I'll observe.
Here. You do for A and B. Do you have the free body diagram for this?
I only did normal force.
Anybody?
Body diagram for 5?
Yes.
I
I tried that.
I did
I don't know if it's right.
I did it, but is it right? Because mine's such a basic free body diagram.
Well, it's not normal.
I didn't know what to call the force, but
Spring force.
that's what I wanted to put. But just know I did it right in my head.
G is not a force. Seriously.
Oh, it's weight.
Yeah, exactly. G is an acceleration. Very good. Right, you can do that.
Alright. You want me to try with this
Very
one?
nice. Is that force of gravity in the x direction? You have that?
So I turn my hand at the XY stuff?
Sure.
Alright.
I'll correct it. It's wrong.
Gonna be doing a lot of corrections.
Because
You are missing a force.
it takes more.
On this one?
Is this friction between A and B?
Friction.
Never mind, you're not.
No, I don't. Well,
That one has two as well.
Oh, yes, I have to have that friction. If I did it,
Bottom one, you only put one arrow, but you will also have two.
okay. Yes, but they're both less than.
Oh, true. Yeah.
Because still.
Yeah, but I'm saying is you have to have
Okay,
two
so I
arrows.
have, would they be the speed of each other?
We don't know. We
If
don't
I
know.
didn't put it inclined, if I didn't put it.
I mean,
almost
logically it
inclined,
makes sense.
Then that would be
Physics,
wrong.
it deals with
Yes,
it.
absolutely.
But you have to go into
Because I didn't put it,
Yes.
just because I didn't put it.
Well, unless you're taking.
Because like everything's right, except I put it straight instead of inclined.
It's fine, as long as you put an arrow that represents this is the x direction, the y direction. You see, you have an arrow on your diagram here, saying this is x and y. If you put an equal arrow x and y, that just means I, instead of putting it tilted, I tilted the paper. As far as I say,
So
but you
then
should, put-
technically I
in the
would be
future,
right.
make it inclined.
Yeah.
Right? If it's an incline.
That's
Just no, erase it.
no.
Yes,
Wait, can I try mine? See if I got it right?
sure.
But it's so confusing. For A specifically, and then that one.
Okay.
I have both, right?
Yes,
Okay.
that's fine, that's it. Okay.
You're the judge.
So no one did this one?
I
I
did
did
that
not
with
even
free
know.
body diagram.
But I just put
normal
So I
force
just
and
point
free
to
body
my
diagram.
free body
Do it.
diagram.
Alright.
I tried. I know, no.
What is this? This is the,
That's Newton, that's plus MG. Excuse me.
it's cosine.
Oh, then I minus them up.
A push is not
both
wrong.
sides are on.
No, yeah, exactly.
So you're saying positive, okay.
That's
It's
all
not
right.
wrong, but I'm gonna show people where this comes from, so let's not write that down, okay? Let's go.
And I'm just thinking a weight arrow is smaller because it's taking over my board.
It gives you credit.
Oh, okay.
Because I was, yeah, just actually name the force. Don't put the form line before. Put force. All right, sit down. Let's talk about this. All right? Did you eat? Oh, it's for the, dude, not even to take stuff out. And who's this? Okay, let's talk about this really quick. So, when you start doing a dynamics problem, the first step is to do a free body diagram where you basically write every force that's acting on the object. How do you do this? If the object is not falling, there's a force counteracting gravity. Remember this, there's always gravity unless the problem says this is not in a place that there's no gravity. Even in outer space there's gravity. All right? There's always gravity. So you always put gravity. Are you with me? Now, if gravity is there needs to be something else what? Counteracting the gravity, right? If it's not falling through something else. So yes, there is weight going down. There is an option. You can either put the weight like this, or you can do what she did, right? Because
Yeah, 'cause
where you split the weight. Because
the y
technically,
direction would be
so it's fine. Either one is acceptable. What you can't do is have both. Right? So you can't put the weight going down and split the weight. So she decided to split the weight into components, and that's fine. Right? He decided to just put one weight, and that's fine, right? But you cannot both split and put the weight. If this was an FAQ on the test, this is what they would do for you. They would say that this right here is 1 point per arrow, and any arrow that's extraneous, that shouldn't be there, they take a point out. That's how they do it. Arrows must touch the free body diagram, they must have arrowheads, and must be labeled. Do not label them with formulas. For example, don't write MG. All right? Or don't write KX here. Actually label them with a name or symbol that's named. Are you with me? So this is the adequate way of doing that. Now this is actually super easy, okay? And I like to split it into components only because it helps me do the dynamics equations, right? But it's easy. Summation of forces equals ma. So let's think about the x direction. X direction. What are the forces acting on it? Well, if I call this positive, who's positive over here? The force of, what is this, by the way?
It's the force of acceleration.
Oh, that's gravity. You already
That's
put
gravity?
it. So we did do
Which
it
is
wrong.
technically weight because.
Oops! That's wrong. He already put the weight, so that's not supposed to be there.
Okay.
Yeah.
Are you with me?
Got it.
That's
Or I can take out the weight, and then I put the weight in the y direction and the weight in the x direction.
Okay.
But you couldn't have the way he had it.
I
So
thought
I'm
was
glad you did it
restricted.
because we did it like that, we can talk about it, right? Now, so you just weight x is going to the x direction, it's positive. This is what? Friction, right? It's negative because it's in the opposite direction. You have to add that all up and equals ma, and that's it,
Why is it extra?
right?
Oh, why?
This is why he called it force of friction.
So I did it.
Right?
We could leave it
But
like
can you
that
put
or no?
this
That's it.
No, because we can't.
All
use
the
weight
now
for-
we cannot use weight, or you cannot use friction.
Excuse me. MG.
Right? So now you have to think about that. But hold on a second. That's not. So no, this is the right way of starting it, but it can't be my final answer because of the problem prompt. Let's do the y direction really quick though. Positive is this way, so it'll be the normal force minus the weight y equals ma. But what's a? Is it falling through the table or going up? No. So in this case, the ma is what? 0. Right? In this case. In that case, there's an acceleration a. Right? So this is the a in the x direction, which happens to be a of the problem. And this is the a in the y direction, which is 0, so therefore it's equal to 0. Right? So now, what is a normal force? Typically, it's just the weight. Why? Because if you solve this, it will be normal equals weight. But this time it's just a weight y. Right? So one way you can straight this equation then would be normal force minus weight y. Now weight y would be what?
Just gravity.
Sorry?
Y direction.
Right, which would be mg. Now at the end of last class I told you that when you split this component is actually sine,
Yeah.
and that's actually cosine, which confuses people because in projectile motion is the other way around. I can do a really quick activity next class. It's going to prove this is true. All right, we'll do that next class because I don't have time and people are not here. But you're going to remember it forever. Yes, we're doing projectile motion and you have that angle over here, right? Then the opposite of Vy is sine, and the adjacent is Vx. But the thing is that in this problem here, right, they're giving you that angle, which happens to be this angle. Are you with me? And you can do this with an activity to prove to you that it is. So that means that the x is actually sine because it's the opposite of the angle. See? The x, right?
So you
You see what I'm saying? So it's the opposite of the angle, so it's sine. So the x direction this time is sine. If it's this angle equals that angle, right? And that's why it has to be sine. So that means this has to be, the way y will be mg sine of theta, right?
If I just
Which
said
equal to 0.
If I said x was sine.
Right?
Said
By the
Yeah,
way,
you said exercise. That's
oops, you're right, cosine. Because this is y direction, right? Thanks, guys. Now, this actually reviews a problem in the prompt. We're supposed to be allowed to use n, otherwise we can't do that. Right? But it's okay. All right. Now, on this case here, it's just that I didn't want this one to be allowed to use n, and that's the problem. That's why I took it out. All right? But that's the final answer for the y direction.
What if we just put negative mg cosine angle?
That's
No,
wrong.
exactly.
You don't have the other force.
But
Right?
I did it good.
If that's happening, then this thing is going through the table magically. Without the normal force in there, nothing's canceling out the weight, and this shouldn't be happening. It should be going to the table, right? Okay. Now in the other direction, weight x would be what? By the same token, it would be mg sine of theta minus the. Now what is friction? Friction is mu, and then the normal force. But what's the normal force according to this? If I set it to the other side, it becomes what?
Cosine.
mg cosine theta. So it should be like this. mg cosine of theta equals ma. Now, did you notice something interesting about this formula? What can we do with that formula if you wanted to? No, M, M, M.
You can factor out.
Alright, no, not factor out. It's in all the terms. So you can actually eliminate M. Right?
But then in the
Now I'm going to show you something even more interesting.
in the y,
Huh?
in the y, you could put mg cosine theta equals negative mg cosine theta, and you
Right.
have to put the number force.
Now, this is not part of our problem, but I'm going to show you something with the mu. I'm going to solve for mu over here. You guys, alright? We'll do it at the end, or just leave it over here. But one more thing I'm going to do here is I'm going to solve for this mu.
Isn't it unsolvable or something?
Oh, no, I'll show you. It's actually very interesting. Now, let's go on to number 4. Right? It's the same principles. Okay? Same principles, honestly. In the y direction, object A will have normal force minus. Now, the thing about this one, though, is that A has a tension. Right? So if I call this positive x on the, so let's do the y direction first. Right? And actually, she's missing forces. But I just realized. She has a force that acts on A over here. Otherwise, A would be going through B. And she has that there. Force normal on A. She also has the component of gravity that acts against B. That's accurate. Right? She also has the component of gravity that acts against GX. Correct? And then she has a force of friction between A and B. And she has a tension. So this one is done correctly. So let's do the y direction. Force.
The force of friction be pushing that way?
Of course not.
It's opposite.
Oh, she is right. He is right.
Yeah,
Because if there was force of friction going that way,
yeah.
Friction force has to oppose.
well,
But that's the thing.
It would get
If it's
pushed into the
accelerating
wall.
this way, the friction's this way.
Yeah, it's
Right,
friction
A
has
isn't
to be
accelerating
opposite.
that way.
But
But what's
B's
on
friction
the
is-
bottom
B's
of it
friction is
is
heading that way.
accelerating that.
B's friction
So
is
that's
heading
why I
that
asked the
way.
question.
So how could
because
the
I-
friction
if
be
B
opposite?
is-
alright, let's do B first.
Way to
No,
make it complicated.
no, that's actually a very good point. We can learn a lot from this. Let's do B first, and it'll help us solve the problem. Let's do the y direction. There's a normal force that's acting on B, but that's not between A and B. That's what I don't like about this.
What do you mean between A and B? I didn't write A and B between that. I wrote A and B as in the weight of A and B. That's what I meant.
Okay, fine. That's a force normal
Yeah.
that's acting here,
Yes.
which is equivalent to the weight of A and B.
Yes, that's what I meant.
You could do that, but you're still missing a force if you do that.
Okay.
But fine, I'll show you. So this is a force normal that's combining the weight of A and B on it. I get what she's trying to say. Or I would have called it the force between B and the surface. Alright? Alright, this force right here. Now, that's positive, right, in our diagram direction. That's the only thing pushing up, yes. Okay, there's nothing else lifting this thing. So what's pushing it down? Well, the weight of B. And she has that there, right? Which would be the force, or I would just put a weight. The weight of B, right? But just the y component of that because it's tilted. Is that the only force pushing it down? That's what she's missing. A is pushing down on it.
Oh, that's
There's a force up here.
Oh, okay.
No, there isn't. You forgot about that. Because A needs to be pushing on it. Think about it. If you don't have A in this one, then where the hell is that one coming from? Because normal force is a contact force. So you just created a force in the universe because it's not paired by the third law. That force is not paired. There's a force pushing A up without A pushing anything down.
Okay.
So this weight that's acting on B has to act back on A. And that's what that is. Are you
So I
with me?
basically just have
But
to
that
do
same
normal
weight
force
needs to
and-
be acting on B. Otherwise, B wouldn't be pushing back on A. Are you with me? So you're missing here. You guys understand what I just said?
Yes.
That there needs to be a pressure that A is applying on that force. So there's also the weight of A, right, acting on top of B.
But AY or A the
AY,
AY.
right? The weight of A in the y direction. All of that equals to 0 because it's not moving in the y direction. So if you clean this up a little bit, the force normal between A and B, right, minus, now what's the weight of B? We talked about this already. It's an inclined plane. It should be mg cosine of the angle, right, where m is the mass of B, right? Be careful with labeling your things. If you don't put mb here, right, you're going to receive the mass of B minus the mass of A, G, cosine of the angle, equals 0. right? So it's very interesting. Okay, now let's think about the x direction. So B is accelerating this way, we know that, so we got to put the ma at the end here, right? What are the forces pushing B that way? Well, that's gravity,
Yeah.
right? So it's the weight
In the x
of B in the x direction, right? The weight of B in the x direction. What else is pushing B this way? Nothing really, right? Nothing really. Could the friction between A and B push B forward? Does that make sense? Or let's think about that. It's very important. The friction that exists between A and B, does it make sense for that to be pushing B forward, or is it going to cause a resistance? Think about it. Because A is tethered to B and there's friction, doesn't that make it harder for B to fall down?
Yeah.
Which means the force of B of friction that B experiences from because of A should be pushing that way.
Yeah.
And it's over there, right? So I'll call this the force of friction between A and B. Has to be negative. But by third law, if that's negative, when we write it up here, it's going to be positive.
Okay.
By the third law, because they have to be paired. Are you with me? I'm trying to say the same reason for which this object was pressing on this one, and therefore we have to have it going up again, right?
So I have to switch it on the diagram to where
No,
the
what?
normal force is.
Right. So
Okay.
because this friction here,
Is on the
if
other
it's
side.
also to the left, now you have two forces to the left combining, they're not canceling each other out, right? So you have to have third law of pairing in the problem. So this will be the friction between A and B, right?
Yeah.
Does that make sense?
Yeah.
Do you see how we have to look at the big picture of the system to figure it out? Remember, that contact forces must do what to each other? All contact forces must what? Cancel out. The car in the road cancels out, right? It always cancels out. So if there's a friction acting on the object, pulling the object back, that means there's a friction acting on the road, pushing the road forward, right? And the reason why it seems that the road is not moving is because it has a lot of inertia, right? And then it makes it look like it's just moving by itself and the force is being created, but it's not. The Earth is being pushed back. It's just such a minute force compared to its mass that it doesn't seem like it's doing anything. All right, so then we have that. Now, we also have the friction against the floor. I'll call it the friction of the surface, all right? And all of that has to be equal to ma. Now let's clean this up into terms that we're allowed to use, right? Because this could be the final answer, but let's do that. Weight of Bx. What do we got here? There would be mg. Weight in the x direction is sine. Remember that on the inclined plane? So by the way, we're looking at weight of b. So m of b, g, sine of theta. All right? What about this one? This is hard because friction, we know, is mu times n. But what is n here? What's the n that applies to that friction? Pause that. Let's go talk about A here for a second. All right? This is the y direction of A. So we have the force of n going up. I might answer your question. That's why I'm ignoring it right now. Okay?
All right.
And then we have the weight of A pushing down. That's it, pretty much, right? All right, and then it equals to 0. Which means we have the force normal of A minus the weight of A in the y direction, which is mg. Y direction in inclined plane is sine or cosine? Cosine. Cosine of theta equals 0. Right? So we have that set up, and that could be our final answer for that one. Now, what about the x direction? Thankfully, we already figured out that this friction needs to be to the right, so now we can do the x direction for that object. And what we have here, pushing, now the object is 0. This is all equal to 0 because it's not going to the left or to the right. We said it's not moving, right? But we still call this direction positive. So we have the weight of A in the, by the way, this has to be the mass of A. Don't forget your subscripts. That can really screw you over, all right? Watch out for that. The weight of A in the right direction plus the friction between A and B. That's right. If A is trying to slow B down to go to the inclined plane, that means B is trying to pull him with it. Doesn't that make sense? Right? That's why the force is acting in that direction, the force of friction. Because if A is slowing down B, what does that mean about B on A? Doesn't that make sense that B is trying to pull A with it? Right? Down the inclined plane? So that's what's happening there. Alright, let's hurry up here. And then we have minus tension, right, equals 0. Right? which
Teachers and
means
students, please
M
excuse
of
this
A
interruption.
of G.
At this time, all boys and girls swim team
Cosine is in the x direction? No, it's the
to the
sine is
office
the x
for
direction.
today's
See, you make
meeting.
mistakes too. You gotta remind
Also,
yourself
please excuse Renee
every time
House,
if it's sine or
Mike
cosine.
Rodriguez,
Plus
Michael
the force
Gutierrez, Jose
of friction
Zamora,
between A and B. Now let's think about that force of
Justin
friction between A and B.
Migueles, and
Force of
Robert
friction is mu
Montesino.
times n.
Again, all
So
boys and
we're gonna
girls
need a
swim
mu
team,
here,
please report to the main office.
right? And that's the mu between A and B, whatever the mu is, right? And then the friction between A and B times the normal. Well, one normal force is causing that friction, just the weight of A, but the weight y of A, right? And therefore, which by the way you can see it over here. Because remember, friction, you can see it on the y direction equation. You see? Because the force normal is just mg cosine of theta. So that's what I'm going to write over there. MAG cosine of theta equals minus tension equals 0. So it's complicated, yes. Don't lose, don't pay attention. Don't get lost here.
Why?
All right?
Why
See,
is it cosine?
because it's coming from here. Gabby, pay attention. You're lost. So you should have told me a long time ago that if you're there, you're lost, struggling. All right? No, seriously, because now I don't have time to go back up. So I have to sit down with you now, one-on-one. Or what you can do is watch this a couple times and follow along what's going on. All right? But remember what I did over here. Okay? We have the weight of A plus the friction. Now friction is mu times n. Mu is going to be the mu between the two objects. And what about the n? N is the normal force that's acting on that object. From the y direction, we see that the normal force that's acting on the object minus g cosine of theta equals 0. Therefore, the normal force can just be mg cosine of theta if you send it to the other side. Okay? And that's what I plugged in over there to get that x direction. But now, going back over here, we have to put now friction between A and B. We have that. It's all right there. That's the same force by the third law thing. So that means I have to write here mu of between A and B times m of A g cosine of theta. And then I have to put the friction between the surface and the thing. I'm going to write it bigger here because it's not fitting the final answer. I'm going to put it here. All right, so weight of Bx. Again, that's mass of B, right, times G, times, remember, x direction is cosine or sine? Sine of theta. That's the weight of Bx. Then I need minus the friction AB. Friction AB is the same thing we put up there. Therefore, minus mu of AB times m of A times G times cosine of theta. That's what we wrote up there, so I'm going to write over here. Otherwise, it's not a paired law, but a third law. Minus the force of friction between the B and the surface. That force of friction follows the same rule. Force of friction equals mu times n. But let's think about what u is. U this time has to be between B and the surface. What about n? N is whatever force is acting on it minus whatever is pulling up. It comes from the y direction. So if you don't forget this, you need to do the y direction because the y direction will tell you what normal force is. And you need the normal force to figure out the friction which applies in the x direction. So that's why you need both directions, because the y direction will give you the normal force equation, right? And you need the normal force to find the friction that applies in the x direction. So in dynamics problems, that happens a lot. Listen to what I just said. Process that, all right? So u of b on s times, now let's think about what is the mass that matters now. According to this, it's all of this, because the force normal that acts on between that surface is going to be all of that. Correct? So that's what I have to write down over here. All of that. Are you with me? But notice how g cosine of theta is in both terms? Isn't it? So I can kind of factor it out. I can put g cosine of theta, and then I put mass of B plus mass of A. So it's as if the mass of both of them is causing that makes sense, is causing the normal force. All right? That's a monster of equation. This is as hard as dynamics gets. Number 5. That is a correct statement. Spring force going up, weight pulling down. Which means in the y direction, I can write down the force of the spring minus the weight equals 0 because it's in balance. The force of the spring, though, is kx. And the weight is mg equals 0. I can just solve that for k now to get my answer over here. To solve that for k, I do k equals mg over x. I did this last class, that's why I did it fast. Alright? That should have been it. Number 6. This is interesting. Let's do a free body diagram for that guy really quick. What is the tension? Tension is in balance. Is it in balance? What is the only force acting on it? Gravity. And the tension. Otherwise, it would be, if it was just gravity, the thing would be falling. So tension has to be acting on it. So there has to be tension, and then what's the other thing? Gravity, weight. So if I do an equation, it's tension minus weight equals 0. Therefore, tension equals weight. Wait for it. On this one, let's do a dynamics equation for it. You go with tension going up and weight going down. Therefore, the dynamics equation will be tension minus weight equals 0. Tension equals weight. Since both of them have the same mass, both of them have the same weight, the tension is the same. What? But isn't the other one pulling it also? So shouldn't be this tension be the mass of this one plus the tension of the other one?
The fully cancels it, right?
No, it's not that. This is pulling too. I hear it's attached, right? Which means there's a tension this way. But that can't be the only force there. Otherwise, we wouldn't be happy to do that thing. It'll be moving to the left, which means there must be another force going that way,
Oh, there's a static friction force for the thing.
holding it in place. Otherwise, that wouldn't be happening. So either way, it's being pulled from both ends. In this case, it's being pulled by the way of the other. In this case, it's pulling by friction. Are you with me then? I like that problem though, because it breaks your mind a little bit, but then you realize why it's happening. Last but not least, these two things are equal. By the third law, you cannot create energy. Therefore, if the Earth pulls on the moon pulls on the Earth, which means gravity is not the force between the Earth. The Earth doesn't pull the moon doesn't pull the Earth. They what? They pull each other, and that's very important. All right, so that's it. Now, you see this monster right there? Physics H covers that slowly. So does A plus physics. Because this is a classic problem when you have to break down a lot of things. More interestingly, set up an inclined plane, just like that one. Get two masses, just like those. Put them on a wall, just like that, and then put a Newton spring here. Measure that. Are you with me? Measure how quickly beef slides across it. You can do this as a lab. Are you with me? You can actually do that. And then be a monster of a grade. But it'd be a cool thing. And you could actually prove things. The last thing I said I was going to do is this. So if you pay attention, next class we'll do ranking tasks together, okay? So the last thing here, let's solve for mu. All right, hold on. Let's solve for mu. M is in all the terms, so I cancel M out. Right? Then I have to bring mu to the side by itself, and alright, because A is on the other side over there. So I'm going to bring that to the other side. So it's going to become, I'm just going to clean it up. mg sine of theta minus mu g sine of theta equals A. Are you with me? Now, if I solve for this, I can do g sine of theta minus A equals mu g sine of theta. Saw that? So solving for mu equals, oh, it was both sine? No, this was cosine. I wrote it wrong. I saw it was weird. Cosine of theta. You see that? Now, I fix it over here too. Cosine of theta. I copied it wrong. Now, if I clean it up, it'll become g sine of theta minus A divided by g cosine of theta. Are you with me? Now, let's say this thing was not accelerating. What does that mean about A? 0. So now it's out. Right? Are you with me? That's how you find the static coefficient of friction, because it's not accelerating, therefore it's 0. So I'm sorry for this. Stay with me for 1 second. Now you see now G is on top and on the bottom. So what that happens? Cross it out. And then we have sine of theta over cosine of theta, which is tangent of theta, which means the coefficient of friction in an inclined plane, the coefficient of static friction, when A is 0 on the inclined plane, is tangent of the angle. Do a lab and prove that that's true.
Why do they say that you can't solve for it?
Of course you can solve
You
it.
can solve for it, it's just like what can't quantify it. Like you can't figure it out.
What I said last class, that what you can't do is you can't derive mu between any two surfaces. But the moment you put a surface on an inclined plane, the mu stops being whatever static interaction there was, and it becomes more the tangent of the angle. So the mu, and this is interesting, this is true for any surface. So you can put an oiled surface or a wood surface or like sandpaper. According to this equation, the only thing that matters is the angle. So as soon as you have an inclined plane, it stops being about the electrostatic interactions between the objects, and it starts becoming about that. And that's really mind-boggling. We'll talk more about it next class, though.
You know we did that lab in like
You turn in our
my
corrections?
physics class
Uh-huh.
on Monday.
Is it?
We did that exact thing like
They're going to do it next class, but they can if they want to.
Turn it in?
What? The corrections? If it's cleaned up and nice, you can turn it in and get a grade for it. Yes. Turn this in, correct it, and get a grade for it. You have to clean this up and understand it. And then you finish it, turn it in.
Can I watch the video and jump in if you want?
Oh, of course. Make it better, make it nicer.